Hey everyone, so this is going to be a recap of our big vector day when we were breaking them down, adding them together, and then applying it to physics and Newton's second law. So our first example here, 1a, is draw these following vectors. Okay, so it looks like we have a total of 6 different vectors here. Okay, they all happen to be 8 newtons, but they're all given a different way to identify where these vectors are. So this first one that we're looking at, I'll box in green, when you are just given so first we have the magnitude 8 newtons, right? So that any vector needs to have a number associated with it in the unit, but we also need the direction, and we're no longer just positive or negative, because when we were positive or negative, we were either working just on the x-axis or just on the y-axis, but now we're going to be able to go anywhere 360 degrees within our Cartesian coordinate. Before we were just staying on the east-west, north-south, but now we can start going in different places. So if you're given just 1 degree, 320 degrees, when we think of our axes this way, right, when you go along, and we're following geometry and conventional math here, this direction here we're saying is 0 degrees, and as you go off to the east axis, and then any positive value is going in the counterclockwise direction. Okay, so anywhere, like if you have an angle anywhere between 0 and 90, it falls in the first quadrant. Okay, and then your y-axis north is 90 degrees. Our east axis is 0 degrees. Our west axis, like directly west, we would call 180 degrees, and then down here is 270 for our south. Okay, so anywhere between 0 and 90 is in the first, anywhere between 90 and 180 is in the second. Then we have our third quadrant, anywhere between 180 and 270, and then 270, and then remember 0 can also be thought of as 360, so 270 to 360 gets us into that fourth quadrant. So if we are 320 degrees, we are in our fourth quadrant here. So if I'm going to draw an axis, and you can draw an axis at any point that you want. Like if you have 2 vectors, you can draw 2 different axes to figure out where your angle is, and we'll see that in a second. So here, if we're going 320, we're going to be winding up in here, 320 degrees. Okay, and this would be 8 newtons. Okay, now if we look, our second is a slightly different green color. Here is now giving a negative angle. Okay, and if all you have is the angle, then we are thinking about our convention that we drew up here. And the positive angle goes counterclockwise, right? Going this way is considered positive. If you go negative, you're going clockwise. Okay, so negative 40 degrees would be going this way, right? Going in the negative direction 40. And if we notice, right, the other angle, if the first green one we drew was 320, the rest of that angle up to the x-axis would be 40 degrees to get back to 360. So if I say positive 320 degrees or negative 40 degrees, I am talking about the same direction. Okay, so this is 2 ways to give the same direction. Okay, now if we switch to number 3, where we're going 40 degrees south of east, okay, what's happening here, notice it's south of, okay, so that means I am going to be going east, and then I'm going to be going 40 degrees south of east, okay, so this 40 degrees south of east is the same thing as saying negative 40 degrees, and remember, negative 40 degrees was the same thing as saying positive 320 degrees. Okay, so we're just having different ways to say the same vector. Okay, now if we go 8 newtons 50 degrees east of south, so there's a difference between southeast and east-south. Okay, so we're going east of our south direction, so I'm going to go in the south, and then I'm going to come in 50 degrees. Okay, and we'll notice, right, 40 and 50 make 90, so between these, right, the 50 is the corresponding angle to the y-axis. So if I go in 50 from the south, or I go down 40 from the east, I'm going to the same spot, right? So 50 degrees east of south is the same thing as saying 40 degrees south of east, which is the same thing as saying negative 40, which is the same thing as saying 320. Okay, we're starting to see a trend here. Now if we look at this, number 5, 8 newtons 40 degrees below the positive x-axis, well, right over here is our positive x-axis, and we are going to go 40 degrees below the positive x-axis, which is the same thing as saying, right, our 50 degrees east of south, which is 40 south of east, which is negative 40, which is 320. So you can imagine what's going to happen with our last example here. Okay, if I go 50 degrees to the right, right, here is our negative x-axis, and this way is to the right, we got 50 degrees going on there. Okay, so it looks like we have 6 different vectors that are going to give us a different direction, but all of these vectors and the ways that we have described the direction all mean the same exact thing. Okay, it is your preference on how you determine the direction that you're going, but if you mean to be in the 4th quadrant like all of these vectors are, and if I can actually write Roman numeral 4, right, if I want to be in that quadrant, if I say that this is 8 newtons 40 degrees, right, 40 degrees implies positive and would get me up here in the 1st quadrant, which is not what we want. So you need to make sure that you are explicit in your directionality, and it is up to you how you want to describe it. Okay, you can use any of these ways, talking about going below or above x-axis. If you go below the negative x-axis, you'd be in here in the 3rd quadrant. So you just need to make sure that you are clear on which direction you are going and which quadrant you're landing in. Okay, all of these are getting the same thing. So all of this to say, what we want to be able to do is, given a vector, we should be able to break it into its components. So let's think about this, for example, 1b, right? So for the above vector, which we all have already established that all of these vectors are the same vector, we want to break it into its components. And what this means, what it means to break into the components, is find the x component and find the y component. And this is where we're using our trig. So however you want to draw your triangle, it is totally up to you. So here is our vector. And it doesn't matter if you use this 40 degrees or you come and use the 50 degrees. It will leave you with the same answer. What it changes, right? So if I do the green triangle, right, here is the y component, here is the x component. If I do the blue triangle, right, here is the x component, and it's not drawn to scale, so I'm sorry about that. I'm pretty bad at drawing to scale. Oops, lost the vector. Oopsies, what am I doing? So here is the x component, and here is the y component. And what you're noticing is you're changing your adjacent versus your opposite side. So if you were to find this over here, which we'll call blue, right, the blue y component compared to the green y component, okay, notice that for the blue, this is opposite of the angle. So in order to find it, we would have to use the sine, right? So the sine of 40 is equal to blue y right, over our hypotenuse, and both of these hypotenuses is 8 newtons, okay, and you don't have to show the unit if you don't want. If we want to do the green y, notice that it is adjacent to our 50 degrees, so green y is going to be equal not to the sine, but to the cosine of 50 is how we're going to find the green y. And again, hypotenuse is 8 newtons. Let me just draw this so that we know that the green goes that way. So essentially, the sine of 40 is equal to the cosine of 50. You're going to get the same answer as you do this. And so it doesn't matter which angle you use. Just make sure you're using the right angle for what you are, for what you are calculating. So I'm going to stick with the blue. I don't know why, I just feel like it, but we're going to get the same answer as we go. Just want to clean this up for us. Oopsies. Ugh. So we got this resultant. So to find the y component, we do the sine of 40 and then multiply it by 8 because we're solving for blue y. So the y component, our force in the y direction, is going to be equal to, your calculator is going to give you a 1.14 newtons, okay? But you have to be smarter than your calculator. Your calculator gives you the right mathematical answer, right? The right magnitude. But notice that our y is going down, right? And if we follow normal convention and we actually just write the convention, okay, positive is up and positive is to the right. So if this y component is going down, I need to make sure that I say we are going negative 5.14 newtons. Another way to say this is 5.14 newtons south, right? They both mean the same thing. I'm going negative y, which we have defined as down, and south is also down, okay? If we want to find the x component, fx, I'm just going to call this fy, get rid of the blue. Okay, so to find fx, now our cosine of 40 is equal to fx over 8, right, because that's our hypotenuse. So solve this, cosine 40 times 8 is going to be, calculator gives us 6.13 newtons. And the thing is, we are moving to the right, which we called positive. The other way you can say this is 6.13 newtons east. Okay, both of those mean the same thing. And if you did not give the directionality on the y and you just said 5.14, people would assume that we went 5.14 up, 5.14 up, and then 6.13 over, and that this is our resultant of 8 newtons, but this vector that I just drew is not the vector that I broke down. So you need to make sure that when you add your components together, they add to the resultant that you had, and just redraw it. And if you see that you are getting the wrong resultant vector, then you just need to double check your sign on your x or your y, or the directionality on your x and your y. Okay, so we're breaking these down. The other thing that we want to be able to do is solve for, if we know the components, we want to be able to solve for our angle. Okay, so let's say that we have an x component of our force of 2.11 newtons east and a y component equal to 4.53 newtons south. Okay, our question is, what is F net? And remember, F net and any force is a vector, so that's why we have to show the direction in which these things are going. So when I get F net, you have to make sure you have direction. So let's add these two vectors where we do the head to tail addition. It does not matter if you go east first and then south, or you go south and east. I'm just going to do it in like normal convention, x first then y, but it is not wrong if you do y then x. So we are going to go 2.1 newtons east of a force, and then we have 4.53 newtons south. Our resultant vector Remember, our resultant goes from the tail of the first vector to the head of the second vector, and we added, right, we drew our first vector, and then we added our second vector from the tail of our second vector starts at the head of the first one. Okay, so we're always doing tails to heads. So here is fnet. So hopefully we are all comfortable with the idea of using Pythagorean theorem to get the answer for the magnitude of fnet. It's going to be equal to the square root of 2.11 squared plus 4.53 squared, right? This is going to give us the magnitude of 5, I've rounded up to 5 newtons, okay? But this is not your final answer because we also need to know the direction. I need to know where we are in relation to our 360-degree flat world, right? We're not in 3 dimensions right now, we're just in 2 dimensions, but you can't give a negative, you can't give a positive because we are not along axis right now. We're in the 4th quadrant, so we need to be able to get somebody to realize where we are. Okay, so when you look at this, we need to be able, we want to be able to solve for this angle. So we need to use the inverse of our trig functions. So here we know, you can use any of the trig functions because we now know all 3 sides, but I'm going to use the 2 values that were given to me in the problem, not the calculated value. It's just a way to make sure that, you know, if you got fnet wrong, you have a better chance of not getting the angle wrong if you don't use your calculated value. So I just use the values that are given in the problem. So this is the adjacent side. This is the opposite side. So adjacent and opposite, this is our tangent, right? I'm just going to write the equation that we have. Tangent of the angle is equal to opposite over adjacent. Okay, so now, before we were using this to solve for the side, like the opposite side, but now we're trying to use it to solve for the angle. So we need to get the angle by itself. We divide through by tangent, which is the same thing as multiplying by the inverse. And your calculators have inverse tangents, an inverse cosine and inverse sine. So that's what we're going to be doing. We're going to say the angle is equal to our opposite side, 4.53, divided by, oopsies, I don't want that individual thing, oopsies, 4.53 divided by 2.11, and then we are going to take the inverse tangent of that ratio to get the angle. Super important that when you're solving and using trig functions, you are in degrees, not radians. And I talked about this in class. If your calculator says rad on top and not deg, right, DEG versus RAD, your calculator is not telling you you are cool and you are rad. It is telling you that you are in radians and you are not going to get the right answer. Degrees allows you to do 360. Radians is talking about 2 pi and pi radians. Don't worry about what that means. We just need to make sure that we are in degrees. So if you have a question about that, you can ask me and we can figure out how to get you there. But put this in, and what we should be getting is an angle of 65 degrees. Okay, now going back to our example of talking about how to distinguish our direction, 65 degrees of a positive value indicates going this way. But that is not where this net force is. This net force needs to be in the 4th quadrant. Okay, so the easiest thing we can do right here is we can say that we are fnet, right? Fnet is going to be equal to, don't forget that we need the magnitude, and our direction, real simple, because this is coming down from what we would call, right, our 0 line, okay, our 0 point for where our 360 starts. So I can just slap a negative 65 on here, and that is the angle that I have. And the only time that you can actually call it the negative angle is if you are coming down from the x-axis. Okay, if you do not come down from the x-axis, you cannot use the negative sign. So if you drew your triangle opposite and you went this way and then this way, and here's your resultant, you no longer have the negative, right? So 90 minus that, this would be you would solve and you would get 25 degrees, I think. Yeah. You cannot call this negative 25 because, again, negative 25 would mean from up here. Right? And if this is 25 degrees, but you're talking about here, you haven't actually gotten to the destination that you wanted. So if you got 25, you would have to start talking about, the right of the negative y-axis, or east of south. Okay, so this, another way to write it would be 5 newtons. Let's call this 25 degrees. And we're going south, and then we are going east of it. So we are going east of south. And both of these things mean the exact same vector, like all 6 of these mean the same vector. Okay, so this is being able to solve for the different components given the resultant vector, right, our net vector. This part C is taking our individual components and adding them together to then solve for the net force, or the net vector, where we'd have to use Pythagorean theorem to get the magnitude, and then use our trig functions, our inverse functions, to get the degrees, and then making sure that our degrees really are talking about where this vector is. So when you're looking at the net vector, if you're going negative 65 degrees, you can redraw this and make sure that you're winding up in the same quadrant and you're winding up in the same spot.